Section 3.7, Inverse Functions. So given a function, f of x, that maps inputs to outputs in this way, we have p maps to x, q maps to y, and r maps to z, we can write this as a set of ordered pairs because it's discrete, where px is an ordered pair, qy is an ordered pair, and rz is an ordered pair. Again, inputs and outputs. Now the inverse of f of x, we're going to call it g of y, can be written as xp, q, or yq, and zr. As you can see, the inputs and the outputs are switched. That is, the outputs, or the range, is the domain of g of y, and the domain of f of x is the range of g of y. Often the inverse function g of y is written as f to the negative 1 of x. Now that does not mean 1 over, that's not a negative exponent, that indicates that it's the inverse, okay, which is a very strange notation, but we have to deal with it. When we plot these two functions, f and f inverse, on the same coordinate axes, they are symmetric about the line y equals x, which makes sense because the x and the y are interchanged in that way. Alright, so let's go ahead and look at a mapping of an inverse. Actually, no, let's just consider this function here. There's something different about it. We have p maps to m, q maps to n, and r also maps to n. Now we talked about in our function chapter, chapter 3, about one-to-one functions. Now this function is not one-to-one. Alright, so the inverse is not a function. Okay, so imagine we exchanged this mn and pqr. So if this is f of x, right, then this is going to be f inverse of x. And m maps to p because we are swapping the inputs and the outputs. Q maps to n, so that means n maps to q, and n maps to r. You can see there that is not a function because of that right there. One input has two different outputs. So this function is not invertible, or it does not have an inverse. Alright, so the idea here is we have a function that in some sense undoes another function. Just as addition and subtraction undo each other, they are opposites, they're inverse operations. The two functions, if they exist, f and f inverse, are inverse operations. Here's the official, the formal definition right here. An inverse function. For any one-to-one function, f of x equals y, a function f inverse of x is an inverse function of f if f to the negative 1 of y equals x. This can be written as, and this is the way that we verify if something is an inverse. F inverse of f of x, that's a composition, if it equals x for all x in the domain of f inverse, if it is an inverse of x. So we use this statement to verify or to prove that two functions are actually inverses of each other. Alright, let's move on to an example. We'll begin with one with ordered pairs. If for a particular one-to-one function, okay, that is an important assumption, a one-to-one function, f of 2 equals 4 and f of 5 equals 12. What are the corresponding input and output values for the inverse function? Let's first write ordered pairs for f of x. F of 2 equals 4 means the input, our ordered pair, is 2, our output is 4, and also, similarly, we have the ordered pair 5, 12. If the input is 5, the output is 12. Because the inverse is going to exchange f inverse of y, as I'm going to write this, because it exchanges the inputs and the outputs, if the input is 4, then the output is 2, and if the input is 12, the output is 5. So I want to go ahead and write this as f inverse of 4 equals 2 and f inverse of 5 equals, or of 12 equals 5. That is how we would write that in function notation. Again, I write f inverse of y because my inputs are actually the outputs of f, what I would think of as my y values. Alright, example 2. If f of x equals 1 over x plus 2 and g of x is 1 over x minus 2, is g equal to f inverse? Well, the way we verify that is to take one of these two compositions. One of these, f of g of x, and show that that equals x, or g of f of x, and show that that equals x. One of those two must be true. They're actually equivalent. If you show one, you've then shown both. Okay, so all we need to do is isolate one of those. So I'm going to go ahead and work with f of g of x. So I'm going to work with f of g of x. So I will take f of g of x, which is f of, and my input is going to be 1 over x minus 2. So everywhere I have an input in my function f of x, I'm going to put in that as an output. So this is going to be 1 over, and we have x plus 2. As my input, I'm going to have 1 over x minus 2. All right. Let's make that a little clearer. It's all in my denominator. All right, so the negative 2 and positive 2 cancel out. So we have 1 over x, which is going to be x. So by our definition of inverse, these two are inverses of each other. So the answer is yes. G equals f inverse. Example 3, similar question. If f of x equals x cubed, the cube function, the cubic function, is g of x equal to 1/3 x, and g of x equals 1/3 x, is g equal to f inverse? So again, we will take f of g of x, and we hope to show that that equals x. So that will be f of 1/3 x, and based on our cubic function there, our input is 1/3 x, and we are cubing that, which is going to be x cubed, and that is a 1 over 27, so we'll write that as x cubed over 27. Is that equal to x? Absolutely not. Not equal to x, so no. G is not f inverse. Alright. Example 4. Identify which of the parent functions besides the quadratic function are not one-to-one, and find a restricted domain on which each function is one-to-one, if any. Alright, I'm going to draw a very quick sketch of each one of these here. Alright, we have the identity function. We have the quadratic. We've got our cubic, the reciprocal function. We'll just go with that. The reciprocal squared, something like that with an asymptote. The cube root, and the square root, and then our absolute value. Alright, there they are. Alright, well, one-to-one, we can use our horizontal line test to determine that. So if we draw a horizontal line across these graphs, we should not be able to cross it more than once. Well, the identity function is a real easy one here. Horizontal lines only cross once. This one is one-to-one. We're looking for ones that are not one-to-one. It's actually stated there that the quadratic function is not one-to-one. Right, and a domain for that, let's go ahead and say this, f of x equals x squared. If we restrict ourselves to only consider the right half of this function, only consider the right half, then that part is one-to-one if we neglect the left. So this is one-to-one if x is greater than or equal to 0, or if you just consider x being less than or equal to 0. We're going to restrict it to this. Alright, let's see. The constant function, that one is not one-to-one, because a horizontal line will cross that exactly. Now, is there any way we can restrict that? Restrict our domain to have a one-to-one function? The answer is actually no. This one is just flat out not invertible. It's not invertible because we cannot restrict our domain somewhere and get a one-to-one function. All right. So now let's move on to the cubic function. This one is not invertible. The cubic function is one-to-one. Horizontal line will never cross more than once. The same with the reciprocal function. The reciprocal squared, I could draw a horizontal line right here, cross twice. So let's go ahead and mark that. 1 over x squared. And similar to the quadratic function, this is one-to-one if x is greater than or equal to 0, if we only consider the right half of that function. Alright, so that one was not one-to-one. The cube root is one-to-one. The square root is as well. And the absolute value is not. Same idea. F of x equals the absolute value. That is one-to-one if we restrict ourselves to only the right half of that function. In that case, it's the identity function. Alright, let's go ahead and move on to number 5. Actually, let's box these in so they stand out. So there will be several times where we must restrict our domain in order to have an inverse. We'll run into a couple of those here in a few minutes. If f of t, a function, is given in this table, showing distance in miles that a car has traveled in t minutes. If that's shown there, then we want to find and interpret f inverse of 70. Well, f inverse of 70 means that my output is 70, and that would match with my input of 90. So f inverse of 70 equals 90. What that means is that traveling 70 miles takes 90 minutes. Or you could say it takes 90 minutes to travel 70 miles. That would be the same statement. All right, so f inverse of 70 means our output is 70. Keep that in mind. All right, a function g of x is given in this graph below. Find g of 3 and g of negative 3. Or g inverse of 3. G of 3 means my input is 3, so I'm going to go to where my input is 3. Check up here, my graph has an output of 1 at that point. So g of 3 equals 1. G inverse of 3 means my output is 3, and I'm doing the same thing. Go over my graph and see what the input is at that point. The input appears to be 5, so g inverse of 3 equals 5. Remember, my input is 3 in the first, and in the second one my output is 3. That's an important distinction. Alright, find the formula for the inverse function that gives Fahrenheit temperature as a function of the Celsius temperature. So here's our function, c equals 5/9 parentheses f minus 32. That's a quantity there. To find the inverse, we want to isolate f. We want a function that's in terms of c. So the first thing we will do is multiply by 9/5. That is the reciprocal of 5/9. That will reduce so that we have 9/5 c equals f minus 32. To isolate f, we'll add 32 to both sides. And because those are not like terms, we have the function f equals 9/5 c plus 32. That's our inverse function. Now, next we want to find the inverse of this function. F of x equals 2 over x minus 3 quantity plus 2, or plus 4. This one will take a little bit more work. All right, so how I'm going to do this is actually rewrite, first of all, f of x as y. Y equals 2 over x minus 3 plus 4. I'm going to solve for x here, so I'll subtract 4 from both sides. So y minus 4 equals 2 over x minus 3. Now multiplying by x minus 3 and then dividing by y minus 4, x minus 3 equals, so multiplying by x minus 3 and dividing by y minus 4. There's the way to write that. X minus 3 equals 2 over y minus 4. And then we will add 3 to both sides so that x equals 2 divided by y minus 4 plus 3. Alright, so the way I would write this, or there are two ways actually I can write this. I can write this as f inverse of y equals 2 over y minus 4 plus 3, which means this function takes inputs of y and gives us the outputs, which were our original inputs. Or we can write this as f inverse of x. This is just a change of variable. Let's actually change the variable. That would help, right? Either of those are acceptable. I prefer the first, but often we use the second so that we can graph them on the same coordinate axes. Number 9, same idea, find the inverse. So we'll say y equals y equals 2 plus the square root of x minus 4. Subtracting 2 from both sides, y minus 2 equals root x minus 4. Squaring both sides. Okay, so because we're trying to isolate our x in this case. Y minus 2 squared equals x minus 4, and then we will add 4 to both sides. So that I'll rearrange this. X equals y minus 2 squared plus 4. Alright, so f inverse of x, I'm going to go ahead and switch. I'll go ahead and switch my variables and say f inverse of x equals x minus 2 squared plus 4. Now I want to point out that my original function here had a domain of x greater than or equal to 4. So 4 to infinity. and a range. Based on our transformations, I can see that it's going to be greater than 2. So this function is going to have a domain of 2 to infinity and a range of 4 to infinity, because the domain and the range will be interchanged when we find an inverse function. Right now, for our last question, given the graph of f of x in the figure below, sketch the graph of f inverse of x. All right, so one thing we know, and I said this earlier, but this is going to be reflected about the line y equals x. Okay, here's the line y equals x. All right, we're going to reflect this across that line. That is going to put a point, well, see how we have 0 or 1, 0? We're going to have a point 0, 1. We have a point 2, 1, so it'll be a point 1, 2. We have a point, and it looks like it approaches the y-axis, so this function will approach the x-axis, turns there, and it's going to continue in that fashion. So if you turn your head 45 degrees to the right, you can see that these are a reflection of each other across that line. That indicates that the x and the y, the inputs and the outputs, are reversed. That brings us to the end of this section. So double check at the very beginning, go back and look at that equation that we used to verify, and see if you can tie how that is related to this last question, because they are very much related.